All right, hello everybody. I'd like to talk today about something that a new kind of parsing architecture that Aaron has basically pioneered and that I've been exploring, and let's just dive right in. So the background, what we should have in our head right now is basic recursive descent parsers. And the whole suite of techniques that we use just for traditional context-free grammars and parsing. And there are some sharp edges that say recursive descent parsing or LL parsers present that we would really like to overcome for more difficult problems. So like one in particular, there's sort of these context, you have limited context in recursive descent. So like error handling is known to be, is quite challenging. Yak, for example, produces terrible error messages. Type inference tends to be split out into its own phase, and you have to have like introduce this cut point, and you have to limit yourself to the kind of computations you're doing in parsing. And then doing sort of like static analysis or even like injecting some of your knowledge from analysis into your parser is kind of blocked from because of these limited contexts that you have. Then there's some pretty sharp edges around affordances too. Like debugging can be quite challenging whenever you have like a very deep call stack and you're jumping around between all of your mutually recursive functions. Then your the behavioral reasonability, it's like in order to figure out how particular inputs will affect the runtime behavior and the sort of data flow through your program is not just manifestly obvious. And then if you want to make some sort of change to your input language, if your problem domain is not completely formalized and you're trying to you're incrementally wanting to implement it, or even if it is formalized and you just want to go piece by piece and implement it, it's somewhat challenging to make incremental changes in knowing what effects they're going to have. And then finally, the scalability of these languages, and this is more like sort of, especially whenever you don't have a formalized system or you're thinking about expanding out, it's quite challenging. Like to reason about performance, I mean, performance on parsers is not. I mean, we've had talks about that today, so we know that's a challenging problem. Your platform independence. We want to be able to run parsers on GPUs, CPUs, on distributed systems. We want to be able to have all of those things, but it's not a solved problem. And then have scale between your domains. So like if you have if you start off with some business problem or some non-formalized problem, and you can come up with a small little hack like some regex to solve it, and then over time it gets more complex, and you start to implement. You run into a context-free grammar, and then sometimes context-sensitive grammars, where your problem is just hard to scale with these traditional techniques. So we have this trifecta of context, affordance, scalability that gives us these problems, and that's what we're trying to address with this nano-parsing architecture. But first, let's look at some of a particular instance of this. We are looking at APL, but it's not limited to APL. I mean, I've written a YAML parser using this technique, and I use the same technique to implement the MetaMath language parser. But APL in particular has a very perverse context where there's runtime parse errors. So there's the famous ABC problem where depending if you have A, B, and C are different variables, the parse trees that can generate of the string A, B, and C has a combinatorial explosion. There's like 10 of them. And then there's mixed scope, there's dynamic and syntactic scope, or lexical scope that sort of interplay in between each other. Then there's quite adverse affordances to parsing APL as well. There's like no and extant parsers do exist, but they're not so great. And there's no black box introspection on sort of like in production systems these days. There's extensive eval usage in production code. It's all over the place as standard techniques. And then there's no formal specification of the language. And in fact, the standard implementations are known to be buggy, so we can't take any particular implementation and call that the ground truth. And then we have quite some challenging scalability issues in APL for an APL parser. There's millions of the code bases in production right now have been around for decades and have millions of lines of code. These are legacy systems, so that means that we're running on multiple different platforms, and we have multiple different dialects of APL that might be mixed in together in the single code base. And then the language is not context-free. So what do we propose? We propose nano-parsing. And so let's zoom right into what that is. So the catchphrase for this is we transpose the computation over the data, atop the data, into the data atop the computation. So in a traditional recursive descent parser, you have like a little window of context. You're a window of like k around whatever token you're on, and you have your entire recursive functions, and you perform a whole bunch of computation over that little window, and then that window slides along. Whereas in nano-parsing, we flip that on its head, and then we take a small piece of computation, and then run that over the entire input. And then we do that again and again. So we're doing multiple passes, but each of those passes are really tiny. That's why it's called nano-parsing. So it's a chain of these back-to-back nano phases or nano passes that they maintain. In this particular, maintain a global state of the parse tree that incrementally refines what your AST looks like. So instead of trying to like insert tokens into an existing sort of empty tree, you can start off with different tree structures and slowly refine that to get it closer and closer to what the actual language implements. And then since we're using APL, we use a lot of APL codefund style tree wrangling sort of techniques. So there's the using a parent vector or even just a depth vector to represent your trees, and then a bunch of idioms that are sort of manifestly data parallel to implement tree wrangling stuff. So yeah. And so this is kind of what it looks like. So you start off with this APL function up top. You can feed this into codefunds, and this was like a recent implement or recent commit of codefunds, and you can throw this at the top, and we entered at a few breakpoints, and then you can just output these different trees at different points through the parser after certain phases. So like at level 1, you see after the lexer, right? But what's interesting is like the lexing itself is not normally lexing just like gives you a stream of tokens. But you can see here we kind of have a little bit of depth information. We kind of have a tree. I mean, it's pretty stubby forest here, but we have that. And then go to phase 2 after we parse brackets. You can see we get a little bit more depth information, right? And then after function specialization, you can see that we have 2 subtrees here that are isomorphic to each other. Sort of like different specializations of the particular function that we defined up there. And then at the end, we get this complete AST. Max, yes?
Can you tell me what each root of the tree does? The different...
The namespace.
Yeah. So, okay, what about number 1? On the bottom, there's like two branches and 2 branches.
Right, those are the functions. Right, that's the function f, I believe, up there, right, that we define. Okay, so this is APL. Bask in its glory, right? This actually is not an APL parser. This is from my own YAML parser. This is the entire parser, right here. Like this is it, and it starts from, and the data just flows from the top to the bottom. So you get a list. You just get a list of characters from the top. Phase 1 normalizes the input, and then each line is a phase of the parser. And you're not expected to understand this, right? I mean, it's written in a way so that someone who knows the problem domain well, and after we talked, like you would be able to sit down and read this code and glean information about YAML and about certain different constraints and novel type theoretic information about parsing parsing YAML by reading this. But it's straight. It's just every single line. The basic thing that I want you to get out of this, other than fancy pictures of a lot of APL, is that it's just from line 1 to 22. Each line is a particular phase, and then it refines the AST as we go down. And I'll move on to this is an excerpt from Cody Funds. So now at this point this is parsing APL, but this zooms into a single phase. And in the parser, like previously where we saw each phase was just like in my semi-toy implementation here of YAML parser, this is, a more complicated. You can see it's multiple lines, and even though it's a single phase. But we have a bunch of interesting things going on here in our parser, right? So one, you can see there's several different places where we're doing error checking. And these error checks will like underline in your code and where your problems are and give you very nice error messages at those points. And then through here, so what this piece of code is, just a standard problem for finding your regions of brackets and parentheses, right? And then it's going through finding the regions where for each expression where those might occur, and then inside this block here, it's going through there and finding the parentheses and adding the type information to some global state. And what's interesting is that we can have this interplay between where we have a local view of our data, where we're looking at each individual expression, and we're just zoomed in on that. But then at the same time, we can take the information that we gleaned from those local pieces and inject them into the overall refine our AST by injecting that information into it. And then after this phase is done, then we now have effectively declared a type theoretic change or transformation on our AST. Once we come in, we know that we kind of know what those regions with parentheses and brackets might be. And then when we come out at the bottom, we have this line 13 here is literally erasing the closed parentheses. So because we've already taken that information and we've like wrapped up the stuff inside parentheses and put them in and wrap them up under a node. So we don't need this closed parenthesis anymore, right? So this is sort of has all of these little pieces mixed together where we have global state, we have a linear data flow from top to bottom, but then we have some potential, like each phase can have some sort of internal little recursion on it. Instead of having like global mutually recursive functions, there can be like local recursion happening, but yeah, and other than that, it's a linear data flow, and it has these nice. It's very easy to insert relevant error messages at any place in your code because you have all of the information that you could possibly need, and you can even this signal function here puts like really nice line numbers and underlines and stuff on your error messages, which just beats Yak and stuff like this out of the water. So what does this give us though? Like what are the benefits of this relative to this trifecta of problems that we talked about? Well, we have sort of holistic context at every point in our parser. So like we have orthogonal error handling, like you just saw, where we can insert very relevant error messages at any point in the code. We can perform arbitrary computations anywhere, right? So that means like you can do type theoretic analysis through your parser at any point instead of having to split it out into some other bespoke pass through your AST. And then we have sort of the ability to do global level analysis on our code base. So you can do like static analysis kind of level things and inject some of that information into your AST as you're going through parsing, instead of having to add different sort of cut points where you do like lexing and then you do another traversal with parsing and another traversal with his like optimizations or something. These can be interleaved in a way that's more natural to the expression of the language, where like at this point you have the information that you need. You have certain constraints that you need that you've already guaranteed, and you can just do it at that point instead of having to like split it across different regions of your code. Then the affordance is like actually using this as a developer is actually quite nice. Like this is how I learned APL effectively. And it's, we can do like stepwise debugging, which is really quite nice. You can just set a, if you want to know, if you suspect there's a problem somewhere in your AST and you kind of know where it's happening, like if it's in parentheses or something, you can just put a breakpoint there, and then you feed your input, and you'll stop right at the point where you know exactly that your constraints, exactly what constraints, what your AST should be at that point, and then you can just have all of the tools of your entire language to inspect what your AST looks like, what is the data that's coming in, what are your types, and all of that at that point, which is really challenging in like Yak or something. And then we have, this is basic, and then the linear, since we have a linear data flow, since we have, anyway, we have linear control flow through the entire code base. That means you just start from, like, if you want to know how your data goes in, you just start from the top of the code and you just read straight from top to bottom. Super easy to reason about. There's like almost nothing to reason about in the control flow graph, which is really nice. And then that combined with the debugging makes it very, very nice to just incrementally extend your system, right? So like the way that I implemented the YAML parser was just to write a simple test, like for like empty input, and then come up with the design of what I thought the AST should be for that kind of thing, implement it, and then just slowly, incrementally add little tiny features to my parser as it became, and bring it in parity with the spec. And the YAML spec has this like big document of 211 productions in order to implement it. And standard extant parsers of YAML have to introduce a lot of bespoke other productions on top of that, as you normally do, in order to implement. And it's really, really hard to reason about. But since you can extend it like this, it makes it much easier to implement a parser. The barrier to entry is really low. And then it also is quite scalable. It allows your system to be quite scalable. I mean, using especially these codefund style tree wrangling idioms and stuff means that you're almost manifestly GPU compatible. And then since we have, it's not introducing particular parallelism primitives into your parser, right? So it allows you to be somewhat platform agnostic, right? And so you can sort of especially if you fed this through into codefunds or something, like, and you're using APL, you can have different backends that target different architectures. You can be on the GPU, you can be on the CPU, you can be on other host systems with different architectures or whatever, without having to put your certain parallelism primitives and stuff in your parser explicitly. And then this is tied in, like the last one is incremental expansion, which is more like, so we talked on, it's different than extensibility in the sense that if you have a problem domain that you're trying to solve by implementing a language, you can start out with you tend to start with like a simplified view of what the problem is, and then slowly learn more information about the system. And as your problem gets more complicated, you might start crossing different domains of language classes. So you might start off with like a context-free grammar that you think that you could implement your language with, but then you'll move into something like APL that's context-sensitive. And if you're using traditional architectures, you'll have to sort of, you can't take your tools that you're using from your previous for a context-free grammar and just slowly extend them into like the larger domain. You kind of have to you have these hard points. We have to throw away everything that you were using and then re-implement it because you've crossed into a harder problem domain. But with this nano-parsing architecture, you're not beholden to any of those particular constraints. And so you can incrementally expand the class of problems or the size of the problem that you are trying to attack. I already went through all of these. But there's definitely some future work here. So if you're interested in this and you want to learn it, there's quite a steep upfront learning curve. That's just a cost you can't get away from. And we haven't done like extensive benchmarking on how this relates to a standard recursive descent parser that might be doing something similar. Like naively, you're doing multiple passes over your input, and so you would have, if you have like C number of passes or N number of passes, you would have a constant time increase in the amount of work that you're doing. But like each of these passes are a lot smaller than your traditional recursive, like the amount of work that you're doing on each little window in your recursive descent. And so it's not clear exactly how those two interplay. So we want to do a lot of extensive benchmarking and especially theoretical analysis. How does this relate to an LL star parser or something, or in the LLPQ or LLPQK parsers or something like this, right? And so we'd want to figure out that story and then look for use that knowledge to look for other opportunities for increasing the parallelism in your implementations. So like for Cody funds especially, you have a bunch of different phases and that happen back to back, but if you compile Cody funds with Cody funds, you have opportunities where you could smash those phases back to back, that are back to back, and smash them together maybe, right? And then you can reduce this potential constant factor overhead. There's a lot of, we need to do at platform comparisons as well. We don't know we don't have a theoretical understanding of the different guarantees that, compiling for a GPU versus CPU stuff. We need to figure all of those out. And then more than anything, since this is kind of this architecture is not being used everywhere, I'm sure there's tons of low-hanging fruit and a lot of unknown unknowns. So I really want to get this kind of thing into you guys' hands and to see what you would do with it and how you would explore what it looks like to write parsers in this particular way. Yeah, thank you very much.
Thank you for a nice talk. So the aspect-oriented programming people have these terms, scattered and tangled code. Scattered where one concern gets just spread out over a lot of code, and tangled where you have one particular point in the code and a lot of concerns are competing for it.
Yes.
Do I understand you correctly? It feels like you're addressing and solving that problem in a sense where you get to write this very linear code where on each line you handle one particular concern and it's all very focused and factored in that way.
That's very much my experience of how it feels to use this architecture. I mean, that's very much on point, is each phase you're making these incremental, and this is specific to parsing, right? This particular architecture that I'm introducing here. But you can kind of like, especially if you need to introduce something into your code, you know that the potential things that can affect your code is all the code above you. And everything below you is just irrelevant, right? And so it's really nice to where your concerns might, or what things might affect you. It's much easier to find, and yeah, it's very much related to what you were saying. So thank you very much.
Okay. Right. I'm not sure how fitting of a question this is, but you're sort of comparing Yak, which is a parser generator, so you give it a file for the productions and tries its best.
Yep.
And maybe you have to mess with it a bit.
Yep.
And you're comparing it with a technique for writing sort of handmade parser that might or might not fit the specification. So are you saying that this is sort of a technique that people should use when they want to make their own language and want to roll a parser quickly? Or where would this technique be best applied?
So I think that you can, Yak is really nice if you have a simple language, especially if you just need to knock off something real quick. But if you need something that's production ready, you need to have you want your users to have nice error messages and things like this. Then it turns out that the code that is produced by Yak, you need to do a lot of work on it. So for the kind of problems, I'm proposing that this is in sort of an industrial grade architecture that is both really nice to use, but also has a lot of nice affordances for making a robust system that you can just start getting up with quickly once you learn the architecture.
Okay. And how would you ensure that it's equivalent to what a parser generator would give you? Like if someone does have a specification, then... Oh, yeah, sorry, yeah. That's right.
It's a good question. No, yeah. I want to keep it on time. So the next speaker is it Yuso? Is that the right way to pronounce it? Yuso? On structural under and GPUs.